Yes, all is good. I gave you a thumbs up.
All right, perfect. All right, yeah, thank you for the introduction, and thanks a lot for the invitation to speak today. So, as was mentioned, I'm Justin Connell, a material scientist at Argonne National Lab. And today I'm going to talk about some recent work that we've done looking at anion effects on electrochemical response in magnesium and zinc and copper electrolytes. And as all the speakers, up to now have summarized, there's a lot of opportunity in these systems, and we've really learned a lot over the last several years of looking at these multivalent systems. I'll sort of highlight a few highlights relevant to what I'm going to speak about today. The first of which being some really strong evidence that as we move to reductive potentials, the formation of any kind of monovalent species in these electrolytes can lead to some interesting chemistries, in particular parasitic reactions that lead to decomposition of the anionic species in your electrolytes. In addition to this, it's been shown that species that are present at very low concentrations, even ppm levels, can have a really outsized impact on reversibility. And so we need to pay attention to not only the majority species in the electrolyte, but also things that may be present even at minority concentrations. And finally, as the last speaker pointed out very nicely, the addition of chloride to a lot of electrolytes can really significantly alter solvation structure and magnesium surface chemistry, in a lot of cases leading to improvements in coulombic efficiency. Now, with all of this insight, there's still a lot of questions we'd like to know. In particular, there's been a lot of theoretical evidence that monovalent ions form, but thus far we haven't really been able to show experimentally that they're actually present. And so we'd like to know, do these monovalent ions form and contribute to parasitic electrochemistry and resulting in lower efficiency? In addition, we'd really like to know, what's the specific role of chloride in promoting reversibility in these systems? And most importantly, can we replicate it in other electrolyte species so that we can enable compatibility with high voltage cathodes? Because obviously chloride is incompatible with high voltage oxides. And then finally, beyond how oxophilic magnesium metal is, are there other fundamental differences or similarities between magnesium and other divalent metals that drive differences in apparent reversibility? And really where we'd like to go with this work is to understand, can we develop common descriptors between divalent cations in order to better understand their behavior in different electrolytes and really start to develop predictive understanding of what kind of response we can understand, and importantly, how we use that to develop new electrolytes. So the approach that we're taking in this work is to move away from looking at just sort of bulk plating and stripping response and move towards dilute solutions of the working divalent cations. And we do this in order to access both mass transport and diffusion limited conditions for metal deposition and start to evaluate more mechanistics of the processes themselves. And you throw copper into the mix in the study specifically because you have an experimentally accessible 2+1+ redox couple. So we can start to get some idea of, what does the electrochemical response of a 2+1+ redox event actually look like in these non-aqueous multivalent electrolytes. The other advantage of going to dilute solution is we can use the rotating disc and rotating ring disc electrode methods to look at again, more mechanistic information about the impact of solution speciation on the response. Because we're working with dilute concentrations of our working cations, we need a supporting electrolyte. And in this case, we're going to use a lithium-based electrolyte with TFSI and diglime. TFSI we choose specifically because even though the magnesium chloride and chlorides in general are fairly poorly soluble in these ether electrolytes, in the presence of TFSI, you can actually add significant amounts of chloride to modify electrolyte speciation. The electrolyte itself gives us a wide electrochemical window. Magnesium and copper are very far apart in terms of redox potentials. And the other benefit of using a lithium-based electrolyte is we can use a lithium metal reference electrode to get a uniform referencing scheme between all of our different working cations. And then finally, I'm going to be using a glassy carbon working electrode in all cases. And the reason for this is because it allows us to rule out a lot of other surface-specific effects like UPD, surface-specific anion absorption, and really lets us get at sort of the fundamental deposition stripping response. And just to show sort of what the background chemistry looks like in this electrolyte, you see, we have more or less featureless electrochemical response across the whole window of the different working cations we want to look at. Although we do see the onset of reduction current at about 0.9 volts versus lithium, which matches with some predictions from DFT results that I'll discuss in a little bit. And so we do attribute this indeed to TFSI reduction. But what this means is that there's definitely going to be some background current when we're depositing magnesium, which should initiate about 200 millivolts below this. That does complicate the analysis a little bit. You can see that a bit in what comes. But just to give you a sort of brief outline of what I'm going to talk about, I'm first going to describe the effect of chloride on improving reversibility in TFSI-based electrolytes. And we found basically a very interesting cooperative effect between TFSI and chloride that yields the overall improvements in reversibility in the system. And then I'm going to sort of generalize this effect and show that it's not only active in the zinc-based systems I'm going to discuss, but also appears for magnesium and copper-based systems. And not only that, extends beyond chloride to other mixed anion systems. So to summarize sort of the benefit of going away from more dilute, more concentrated electrolytes to more dilute systems is summarized here, where in this voltammogram of a 0.2 molar zinc electrolyte with a 1-to-1 ratio of TFSI to chloride, the only reason you see a peak in this voltammogram is because the potential is reversed after you initiate zinc deposition. And so it just, as you reverse the sweep, you see a peak in the maximum current, and then you obviously see a peak because you deposited a fixed amount of metal. When you go to a more dilute system, you actually access mass transport limited conditions. And the reason you now start seeing peaks is because of that mass transport limitation. And what this shows is that sitting underneath of these sort of individual peaks in the bulk plating and stripping is additional complexity. And specifically, if we compare the response of this mixed TFSI chloride electrolyte to a TFSI only electrolyte, you see that what's actually happened here is there's an additional redox couple that's present upon the addition of chloride relative to the TFSI only electrolyte. And so because we're working at in dilute conditions, again, we can utilize rotating disc and ring disc electrode techniques. And just as a brief refresher for those who may not be super familiar with these techniques, the idea of an RDE measurement is you have a cylindrical electrode that's embedded in an insulating collet. And if you induce rotation of this electrode, you can force convection of your reactants to the surface of the electrode and essentially set up a constant delivery of your active material to the electrode surface. And the result of this is that instead of seeing peaks in this mass transport limited case, you actually start to see plateaus corresponding to a diffusion limited delivery of your active species to the electrode surface. And what this lets you do via the Kutek-Levitch equation, if you vary the rotation rate, you can actually extract kinetic and thermodynamic process parameters related to the process that you're studying. Rotating ring disc, it relies on basically the same setup, but with the addition of a ring electrode to the outside of your working disc electrode. And what that allows you to do is sort of generation collection experiments, where as you generate or consume a species of the disc electrode, you can monitor perturbations to the current on the ring electrode as you generate or consume that species at the disc electrode. In this case, we'd be consuming as we consume zinc or whatever species for metal deposition. You would see a decrease in the steady state current at your ring electrode. So the really interesting thing is as we start rotating in these mixed TFSI chloride electrodes, we see two diffusion limited plateaus in the voltammetry. And this second diffusion limited plateau occurs after zinc plating initiates. And what we see is that what appears to be the case is that there are two separate nucleation overpotential events as you go to more and more negative potentials corresponding to two separate initiations of zinc deposition. What we also see is that both of these reduction plateaus exhibit Levitch type behavior. So they exhibit a linear increase in the limiting current density as you go to higher and higher rotation rates. And so this suggests that definitely multiple species are active in the system. But to confirm that they are indeed related to zinc deposition, this is where the ring disc technique comes in very handy, where as we drive constant zinc deposition on the ring electrode by holding the potential at 2.1 volts, so corresponding to this first reduction plateau where we know zinc metal deposition is taking place, we see that as we go to more and more negative potentials, we see a decrease in the ring current corresponding to consumption of zinc by the disc electrode. And we see both two distinct decreases in that current density decrease, indicating that both of these reduction events are related to the consumption of zinc at the disc electrode. I won't show it here, but if we do a corresponding experiment where we hold the ring electrode at very positive potentials, we don't see any evidence of reoxidation of a solution species such as a monovalent zinc ion. So we don't really see any evidence of zinc plus formation. So what the voltammetry tells us is that there are multiple solution species that are leading to the deposition of zinc metal in this system. And so to understand what's driving this behavior, we can start playing around with the solution composition. And so what I'm showing here in this scan is focusing only on the reverse scan. So where deposition ceases, more or less corresponding to the thermodynamic potential for metal deposition. As we play around with the chloride concentration, we see two very interesting things happening. The first of which is as we increase the chloride concentration, the magnitude of the current density associated with this first reduction plateau decreases, suggesting that in order to access the full current density accessible in the system, you have to go to more and more, or higher and higher over potentials, more and more negative potentials. Correspondingly, as we increase the chloride concentration, though, we see the onset of metal dissolution shift to lower over potential, more negative potentials. And so what this suggests is a cooperative effect between TFSI and chloride that's resulting in the overall more reversible electrochemistry in the system. And to illustrate what I mean by that, we can return to this idea of there being essentially two overlaid redox couples, where if we highlight the TFSI-based contribution to the voltammetry, we see the early onset of metal deposition, but a higher over potential for metal dissolution. And why we believe the deposition is able to initiate earlier is due to the relatively weaker association strength of TFSI with the zinc cation. And so it essentially takes less energy to desolvate zinc from a TFSI-rich coordination relative to chloride. We look now at the chloride-based concentration contribution to the voltammetry. We see, again, metal deposition initiating at higher over potential, but the dissolution initiating at lower over potential. And this can be rationalized by the fact that the chloride relative to TFSI is more strongly associating. And so there's essentially more free energy released by reassociating a zinc ion, a cation with a chloride ion in solution. So there's a higher driving force to resolvate zinc into a chloride-rich speciation rather than a TFSI-rich. And so if we then sum the contributions, this is what leads to the overall more reversible voltammetry that we see in the bulk plating and stripping behavior. And you really wouldn't have been able to rationalize this if you hadn't gone to the dilute case and been able to pick out the individual contributions of the ions. Now that said, this is at this point a little bit speculation based just on voltammetry. And so to determine whether this effect is reasonable, we turn to density functional theory to investigate some potential active species that might be leading to this behavior. And so what we did is simulated a variety of different zinc coordinations with varying numbers of TFSI, chloride, and diglyme, TFSI, chloride anions, and diglyme solvent molecules in the first solvation shell. And basically, in order to down select, we rule out any complexes that were either unstable to one electron reduction or that yielded reduction potentials outside of the window where we see any evidence of zinc metal deposition in our voltammetry. And what we find is several stable complexes, and I'll highlight a couple of them here. One set of complexes which are chloride-rich, where we either have zinc sulfated by a diglyme and a single chloride anion, or zinc sulfated by a chloride anion and a TFSI anion. They both give relatively similar reduction potentials. What we also see is several stable TFSI-rich coordinations, with one TFSI and one diglyme, or with two TFSI anions, both again giving fairly similar reduction potentials. And what we see is that the trend predicted by DFT matches very nicely with what we see in the experimental results, where the TFSI-rich coordinations predict reduction onset positive of that with the chloride-rich coordinations. Not only that, these structures actually match very well with the experimentally observed thermodynamic reduction potentials that we see in the voltammetry. And so what this says is that this idea of the cooperative effect between TFSI and chloride leading to the overall more reversible electrochemistry does appear, in fact, to be a reasonable hypothesis. So while this cooperative effect is exciting, the next question obviously is how far does this effect extend? Can we bring this to other systems? And of course, there's a magnesium ion conference, so of course I have to talk about magnesium. And so we wanted to see, first, does this effect extend to other working cations? And what we see is that indeed, if we add chloride to a TFSI-based electrolyte, we see more or less identical behavior for copper, zinc, and magnesium. We see the appearance of additional redox features upon the addition of chloride, both for copper and magnesium, that look very similar to what we see in the zinc systems. No, we'd also like to know, I made the point at the beginning of my talk, can we mimic what chloride is doing? Does this effect extend to other anions? And so to understand what trends we might expect, we turn again to DFT, and we see that as we start to play around with anions of differing association strengths, we do see a consistent trend of a shift in the redox potentials. We move to more strongly associating anions like chloride to very weakly associating anions like PF6. And we expect very similar trends for both zinc and magnesium. So we want to know, to what extent can anion association strength really be used to tune the reversibility of metal plating and stripping? And so we begin by exploring a sort of chemically similar anion to TFSI, this Triflate anion shown here schematically on the bottom left. what we see is that for both zinc and magnesium, we see very similar behavior for both the mixed TFSI chloride and triflate chloride systems, where the magnesium more or less looks identical, where we see 2 oxidation features and 2 reduction features in direct analogy to what we saw with the zinc system. But very interesting for the zinc triflate system, while we again see 2 distinct reduction events, we only see 1 obvious oxidation feature. And so what this seems to suggest is that the addition of triflate, the combination of triflate and chloride shifts this second dissolution event to a potential very similar to that of chloride. And so the question here is, can triflate be used to mimic chloride? Can we start to move away from chloride in these electrolytes to improve the versatility of these systems? And so if we compared the plating and stripping of just the 2 constituent electrolytes, so TFSI only in the black and triflate only in the blue, we see that the whole redox event appears to shift to lower overpotential, consistent with the higher association strength of the triflate anion. And so, to answer this question, can triflate be used to mimic chloride? We see the answer is actually yes. Where in direct analogy to the mixed TFSI chloride system, we see 2 distinct oxidation features in the mixed TFSI triflate system. And if we overlay the voltammograms I just showed, we see that this first oxidation event overlaps exactly with that of the TFSI only system. But this lower potential peak sits directly in between the 2, the triflate only and the TFSI, suggesting that there is mixed TFSI triflate coordination in the system, in some contrast to what this appeared to be distinct populations in the TFSI chloride system. We also see only 1 obvious reduction wave, which is again consistent with mixed coordination driving deposition, and the location of this peak is again directly intermediate to the triflate and only in TFSI only cases. Now, this isn't just relevant to the dilute case. If we could look at now a bulk electrolyte, a 0.2 molar zinc electrolyte with the TFSI or triflate only, and then the mixed TFSI triflate system, we see essentially the exact same trend, where we see improvement in reversibility relative to both electrolytes and the onset of oxidation, again, sitting intermediate to where we see for the TFSI only and triflate only cases. And so we very strong evidence that this cooperative anion effect appears to be active for both the TFSI chloride and the TFSI triflate systems. So we return back to the predictions of DFT and we start to compare anions of differing association strength. We see, what I've already shown to now, the TFSI chloride and TFSI triflate case, we see the additional oxidation event to lower overpotential relative to the TFSI only. If we move to more weakly associating anions, though, very interestingly, we see the location of this additional oxidation event shift to higher overpotential in direct analogy to what we see and what's predicted by the DFT. And interestingly, in the case of PF6, we also see the onset of reduction start to creep more positive of that with the TFSI only system, which is, again, consistent with this idea, because with a more weakly coordinating PF6, it should be even more easier. It should be more easy to desolvate zinc cation or desolvate cations relative to TFSI. And again, as we saw before, in the TFSI triflate case, all of these mixed anion electrolytes it result in improvements in reversibility relative to the TFSI only case. Again, in keeping with the predictions of DFT, where we see improvements in reversibility of greater than 200 millivolts for all the mixed anion electrolytes we've studied. And so what this tells us is that anion association strength can really serve as a descriptor for reversibility of metal deposition. And more importantly, it suggests a new set of design rules for electrolyte development. These systems that we chose here certainly aren't optimized. There's a long way to go between what we have with these triflate and PF6 relative to what chloride can do, but we're moving in the right direction. And it suggests that we can really start to think differently about how we design electrolytes, where we don't have to get everything from one anion. We can start to design independently what's guiding one half reaction versus the other. So to conclude, it's shown that divalent metal deposition really involves a complex interplay between the different anions present, highlighting specifically the TFSI chloride system, where the overpotentials for the deposition and stripping half reactions can really be controlled independently based on the specific anions. And via their cooperation results in lower overpotentials for plating and stripping and improvements in clogging efficiency. We've shown that this anion association strength can serve as a common descriptor for reversibility of multivalent anodes, where this effect appears to be active for all of the anions and divalent cations that we studied in this work. And again, as I mentioned, this suggests a new set of design rules that we can use to develop new electrolytes. And the one comment that I'll leave with is that, what these results seem to suggest is that interfacial speciation likely differs significantly from that we see in bulk measurements of electrolyte composition, as even, these very weakly associating anions like TFSI and PF6 in particular appear to participate very strongly in both the plating and stripping reactions. And so even though these species appear to, form solvent-separated ion pairs in the bulk electrolyte, clearly they begin to associate it more tightly with the cation as they approach the electrified interface. So we have to think more about that as we move forward in our understanding of these electrolyte systems. So with that, I just want to acknowledge everyone else who contributed to this work, and the facilities at Argonne as well, and obviously the funding from the Joint Center for Energy Storage Research. And so with that, I'm happy to take any questions.
Thank you very much, Justin. We have time for a discussion. So in case you just joined recently, if you're a regular attendee, you can post your questions on the Q&A section, a special question answer window, where you can submit a question in writing. Please address your questions to the panel. If you are a panelist and you would like to ask a question, just unmute yourself and speak up. And Max is going to take your questions and read them out when you post them.
Yeah, thank you very much, Justin. Very nice and also very valuable, I think. I mean, we all had the chloride in mind when it comes to improving the reversibility, but chloride is corrosive, and if you can substitute that by a different anion like TFSI, this is of course actually a new field that you open here. Yeah. I see two questions at the moment. One is from Samuel Bertolini. Nice presentation. One question about the calculations.
I think that was for the previous talk. That was to Jean-Sébastien.
I'm sorry.
And it was already answered by Jean-Sébastien. I think we have no questions on the Q&A at the moment.
That's correct, yeah. Sorry, I just saw them.
Oh, there's one. There's one now.
There's one now. What about the solvent effect from Vidianat?
Yeah, that's a really interesting question. So, especially thinking as we go to more, weakly associating anions, thinking about, carborane or the borates or alkoxy-aluminates, at some point anions are going to become too weakly associating, and the solvent is probably going to start to take over. And so, yeah, or just playing around with solvent chemistry. I mean, here we focused only on diglyme, but as we move, from the different length of chain glymes or other solvents completely, yeah, I imagine that the solvent will also at some point start to participate in these reactions. And so it probably represents also a sort of a third knob to turn here. Second knob.
Okay. So did you use this effect already to really build cells and cycle these cells and you find differences, or?
So far, no. I mean, we're still sort of the early days of tuning this chemistry. I mean, the specific anions I chose even are just basically what I could buy on Sigma. Or, we had some great collaborators who were able to synthesize a couple of these salts, custom for us. And even with that, but I don't get into it here, but impurities in the electrolyte also really dominate. So the point I made at the very beginning of my talk. I mean, water obviously is a big problem here, but other residual impurities from the synthesis, residual halides, residual other cations, all these things play in. And so there's sort of two things that have to be tuned here. One is obviously this anion association effect, but also the purity of the salt has to be really tightly controlled. And so getting salts of varying enough chemistry and also high enough purity is something else we really have to pay attention to here. And so that's something we're actively working on, obviously, but in terms of going to full cells, it's getting a salt that's pure enough to really you'd be certain that you're not doing some other parasitic chemistry is definitely a big challenge.
I think purity is something which is really disturbing us sometimes.
Yep.
Because, you find some strange effects, but this is not due to our main compound, because this is just some spurious things that come up by some ingredients. Okay, thank you again. I don't see more questions here, so then I would like to move on to the next speaker.